All right. Hello, everyone. Welcome to the second lecture of our Introduction to Modular Forms. So last time we covered some of the basics of group theory that we'll need. And towards the end, we defined what a holomorphic function is. And so I'm just going to quickly, I'm just going to quickly go over the definition of a holomorphic function. So let's say we have a function f from an open subset of the complex plane. So U is an open subset of the complex plane, and I have a function. I have a complex valued function that takes inputs from the open set U, and then I can write this function as f of x plus iy equals u of xy plus I v of xy. So the u and v are the real and the imaginary parts of f, respectively. Now, so we had two equations which we named Cauchy-Riemann equations. That is, the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y, and the partial derivative of u with respect to y is equal to the negative of the partial derivative of v with respect to x. So we defined. We saw a theorem that a function is differentiable at a point if and only if all the partials exist and are continuous and the Cauchy-Riemann equations are satisfied on that point. Then we define a holomorphic function. So f is holomorphic if f is differentiable at all z in U. So yeah. All right. So now all the functions I will be considering today, so they are of this form. The domain is an open subset of the complex plane, and furthermore, we shall be requiring that this U is connected. That is, if I try to sort of draw the domain, so let's say the interior of this thing, this is our domain. So I'm not going to define what a connected set rigorously, but you get the idea, right? So if my domain is this and this, then we would say that our domain is not connected. So I think an intuitive idea of what a connected set is okay for our purpose. Sorry. So yeah. All right, so now we are going to define what an analytic function is. Yeah, sure. Well, not really, because we'll need the fact that U is connected in order to prove some of the later theorems. That is, if let's say if all the derivatives vanish at some point, then the function becomes constant, which we shall see. So for that theorem to hold, I need my domain to be connected. Because if my domain is not connected, so let's say in this connected part, it is defined in a certain way, and in this connected part, the function is defined in another way. So then the theorem does not hold. So for some, how should I rephrase it? So for certain results of complex analysis to hold, I need the fact that U is connected. All right, so sorry. Now, what is an analytic function? Function. So we shall call a function analytic if is analytic if for all points in the domain there exists an open ball. So that is, if this is my open set U and this is a point inside my open set, then I can find an open ball like this. There exists some R greater than 0 such that F has a power series in this open ball. In let's open ball centered at Z0 with radius R. Okay, so this is how we are defining analytic function. So, let me clarify what do I mean by power series. So, by power series, I mean a series of this form. Let's say an z minus z naught to the power n, where this sum runs from n equals 0 to infinity. So a sum of this form is called a power series, which is centered at z naught. All right. Now, there is a very, very beautiful theorem in complex analysis that says that all the holomorphic functions are analytic and vice versa. So
why do we have?
because you see, holomorphicity is kind of a generalization of differentiability for complex functions, right? So if I have a function that is differentiable, so if I have a if I have a real function that is differentiable, the function is not necessarily analytic, but in complex analysis they are equivalent. So the theorem says that holomorphic. So as I said, holomorphicity is a generalization of a differentiable function in complex numbers. So the theorem says that a function is holomorphic if and only if it is smooth. What do I mean by smooth? By smooth, I mean that the function is infinitely differentiable. So I can differentiate it as many times as I want. And for complex analysis, this is equivalent to being analytic. But for real functions, well, first of all, differentiable is not equivalent to smooth. So differentiable does not mean smooth. And smooth as well does not mean analytic. So this is in R, and this is in C. Okay, so one example for the fact that a smooth function may not be analytic for real functions, that is, let's say I define a function like this: f of x equals e to the power negative 1 over x squared if x is non-zero, and that is 0 if x is 0. So this function is smooth, and so by smooth I mean that this function is infinitely differentiable at all the points at all the. No, this is not a bell curve. So bell curve is e to the power minus x squared. This is e to the power negative 1 over x squared. So this is not a bell curve. And you can prove that all the all the derivatives at 0 are 0, right? So if the function had a power series representation, so around 0, then the function would look like something like this: f of 0 plus f prime of 0 times x plus f double prime of 0 x squared by 2, so on and so forth, right? But all these terms are 0. Then we would have that f of x equals to 0 in some neighborhood of 0. But in some, but this is not true. So this is an example of the fact that smooth does not really imply analyticity in real numbers. But we are extremely lucky that in complex numbers, holomorphicity, smoothness, and analyticity, all of them are equivalent. All right, so let's say, again, this is my domain U, and I have a function from U to C, and say Z0 is a member of U. Then, as I said earlier, that we have an open ball that is inside our domain, of course, and inside that open ball, I have f of z equals to some power series a n z minus z naught to the power n, where the sum runs for n equals to 0 to infinity, and this is true in an open ball. All right, and the coefficients of the power series are as expected. That is, a sub n is the value of the nth derivative of f at z naught divided by n factorial. All right, and yeah, so I think we need to talk about the convergence of this power series. So this power series converges absolutely. So by absolute convergence, I mean that if I take take this sum instead, a n z minus z naught to the power n, the modulus of this thing, this sum converges. And this sum also converges uniformly. Converges uniformly. So what is uniform convergence? Uniform convergence. So let's say I have a sequence of functions. Say a sequence fn of functions that are defined on the same domain, and they are, let's say, complex functions. Okay, so this sequence of functions, let's say n equals 1 to infinity. So this sequence converges uniformly to some other function f from u to c if for all positive epsilon, there exists some n, which is a natural number, such that fn of z minus f of z, the absolute value of this, smaller than epsilon for every n greater than, sorry, so this n and this n is not the same. So let's say this is m for every m greater than n, and for all z belongs to the open set U. Okay, so this is a little bit different from the usual convergence, from the normal convergence. So from let's say in the normal convergence, I can have like different epsilons. No, sorry. If I have an epsilon, I can have different m. I can have different n for different z. But for uniform convergence, I have the same n for every z. So this is the difference between like, the usual convergence and the uniform convergence. So for uniform convergence, so as the name suggests, it is uniform in some sense. So for any z, I have the same n. Okay. So is the definition of uniform convergence clear to everyone? So what I mean by that this power series converges uniformly, I mean that, let's say, f1 is the first term, say a0 plus a1 z minus z naught. f2 is, let's say, a0 plus a1 z minus z naught plus a2 z minus z naught square. So this is f2, and we can define fn as the sum ai z minus z naught to the power I, where I runs from 0 to n. So this is my sequence of functions. And this sequence converges uniformly to our function f. Of course, so this converges uniformly to f, but what is the domain? No, the domain is not the whole of U. The domain is the open ball centered at z naught with radius r. So this converges uniformly to F in my open ball. Okay, and the maximum radius this open ball can take is called the radius of convergence of this power series. So if the power series converges in this ball, then it also converges in the smaller ball as well. So possibly we can extend the open ball, but we can't always do that. So the sort of the highest value of R that we can have, it's called the radius of convergence. All right. So there goes the power series, and now we're gonna talk about integration. So when we do real integrations, like we have, let's say this is a function, and we want to find the area under this curve. So what do? We like this. Let's say this is a, this is b, and then we do this f of x dx from the interval a to b. But in complex analysis, we are mostly interested in path integrals. So by path integral, I mean that here the domain I'm integrating over is an interval. But in complex analysis, we are interested in integrals where the domain is a curve. Okay. Well, path integral has a very specific meaning in quantum mechanics, so not that one. All right, let's say I have a holomorphic function from U to C, and I have a curve. So what is a curve? A curve is a continuous map from an interval to, let's say, U. Okay, so this needs to be continuous. And we shall say this is a smooth curve if this is a smooth map. If this is a smooth map, so here we said the curve is continuous. We didn't say anything about the differentiability. So if the curve, if this map is a smooth map, that is, if this map is infinitely differentiable, we call the curve a smooth curve. And you can see that here the domain is a closed interval. So if okay, let's say the curve is a map gamma. So if the endpoints are the same, so that is, if gamma of A and gamma of B are the same, then we call gamma is a closed path. Closed curve or closed path, yeah. So that is if gamma looks something like this. This or this. So if this is the starting point and this is the ending point as well, then yeah. So these are the examples of a closed curve. And yeah, in complex analysis, we are mostly interested in integrals that are over some curve gamma. Okay, so now I'm going to define what this thing is. Okay, so let's say I parameterized gamma by some function, gamma from that is, it's a function from a closed interval to my domain of F. Okay, so what is the definition of this? So we are defining this as an integral from A to B of f of gamma of t, gamma prime of t, dt. Okay, so in order to integrate over some path, I need gamma to be differentiable as well. So yeah, so gamma needs to be differentiable. We have defined a curve to be a continuous map from a closed interval to our domain, but in order to integrate over that path, I need my curve to be differentiable as well. Because if it is not differentiable, then we can't really take this this gamma prime. Okay, and I think I need to clarify one thing a little bit. That is, so so gamma takes real inputs, right? Sorry. So gamma takes real inputs because it's a map from an interval to an open set in the complex plane. So gamma takes real inputs, but it gives out complex outputs. So let's say gamma 1 of t plus I gamma 2 of t. Okay, and these gamma 1 and gamma 2, these are real valued functions. And by gamma prime, I mean that gamma 1 prime of t plus I gamma 2 prime of t. Okay. So this is this. And f of gamma of t, this is also a complex number, right? But we are integrating over a real interval. So how do we define it? So let's say a to b f of gamma of t gamma prime of t. So this gives us a complex number, let's say u of t plus I v of t. Okay, so u and v are the real and the imaginary part of this thing. And u and v are real valued functions. So then we define this integral as, basically we split up the real and the imaginary parts and then we integrate them as usual. dt plus I integral of from a to b of v of t dt. Okay, so these are sort of the basic things about integration. Okay, does anyone have any question?
Previously defined f as the sum of ut and
No, this whole thing, f of gamma of t times gamma prime of t. That is the sum of u of t and I times v of t. Oh yeah, I get it. Like previously I defined f of x plus iy as u of xy and v of xy. Well, we won't really use these things, so I don't think it really matters, this notation. All right, so now we shall do an example. Example, let's say I want to do the integration of 1 over z over the unit circle. So the unit circle is, how do I remove this thing?
undo.
Where is the undo button? Oh, yeah, thank you. Okay, so I'm integrating the function 1 over z over the path that is defined by the unit circle. That is, so this is the path I'm integrating over, and the function I'm integrating is 1 over z. So how do I do it? First of all, I need to parameterize this curve. So how do I parameterize this curve? Let's see. Sorry? Yeah, so yeah, that works. For that, I need my closed interval to be from 0 to 2 pi, right? Yeah, 0 to 2 pi, and pi of t is e to the power it. Okay. Then, yeah, then this becomes, if I use the definition, so this becomes an integration from 0 to 2 pi. So here I shall have f of gamma of t. F of gamma of t. So my f is 1 over z. So 1 over gamma of t. So what is gamma of t? That is e to the power it, right? Then I need gamma prime of t. So gamma prime of t is I e to the power it. Okay, so I e to the power it dt. So this is simply this and this gets cancelled out. So this is 2 pi and this is 2 pi I. So yeah, we have computed the integral of 1 over z along the closed curve denoted by, along the closed curve of the unit circle. All right, so what about the integration of z to the power n along the, let's say, the same curve, where n is not negative 1, because for n being negative 1, we have already done it here. So what about this one? So here as well, we shall parameterize the curve as we did before. Yeah, do you have any question? Yeah. Yeah, the codomain of gamma. Oh, yeah, I should have clarified it. I'm extremely sorry. So this is the complex plane without the zero. So we have taken out the zero because the function I'm integrating, that is 1 over z, this is holomorphic everywhere except the origin. Okay, so that is why I needed to take out the zero from the. All right. Yeah, so here as well, we are gonna parameterize gamma as we did before. So this integral becomes integral from 0 to 2 pi. So in here, we shall have f of gamma of t, right? So that means gamma of t is e to the power it, and that f is z to the power n, okay, times I, so, sorry, times this I e to the power it, I e to the power it. Okay, so this integral is, I can take the I in front of the integral, so that is I 0 to 2 pi e to the power n plus 1 it, right? And we can basically split up the real and the imaginary parts. So we have I 0 to 2 pi cosine of n plus 1 t dt. So, minus integral from 0 to 2 pi sine of n plus 1 t dt. Okay, and both of these integrals are 0 because, well, cos and sine are periodic functions with period 2 pi. So that's why both of these functions, so both of these integrals are 0, so this is 0. So we have established that the integral of z to the power n over the curve that over the unit circle, this is 0, if n is not negative 1. So if n is negative 1, then we would have like 1 in here. Since n is not negative 1, I can split up this exponential into cosine and sine. Okay. Does anyone have any question? All right, so here we can make some observations. So this was the path we integrated over, right? And for z to the power n, the function is holomorphic on the whole complex plane. But for 1 over z, the function is not holomorphic on the origin. So we can say that there is some sort of hole in here. Okay, so if we integrate 1 over z over, let's say, some other curve, let's say this one. So for instance, let's say this one is, this point is 2 plus I, and let's say the radius is 1. So if we integrate 1 over z over this circle, then we would get that the integral is 0. Okay, shall we do the integral? I think it's a good exercise. So our gamma is 2 plus I r e to the power it, right? So times e to the power it. And gamma is, as usual, defined from 0 to 2 pi to the non-zero complex numbers. Okay. Is this correct? No.
Plus I plus
Yeah, there should be a plus, right? Yeah. So my center is here and my radius is 1. So yeah, there's a 1 in front of this e to the power I, right? And the function I'm integrating is 1 over z. So the integration of 1 over z like over this path gamma is 0 to 2 pi 1 over z, that is 1 over, so here I shall have f of gamma of t. So f of gamma of t is 1 over 2 plus I e to the power it. Sorry, plus e to the power it. I'm extremely sorry for that. Plus e to the power it. Right. Then I'll have the derivative of gamma. The derivative of gamma is I e to the power it. Right. Uh, okay, so how do I do this integral? Say, 0 to 2 pi 2 plus I e to the power minus it plus 1 dt. Okay, and here, well, you have, so this can be split up into cosine and sines, and then you can do the integral. So after doing the integral, we'll most probably get a 0. Well, we will get a 0. Okay. Well, I don't really know how to do integrals, so I'm just gonna skip it and say this is left as an exercise. Okay, so let's believe that this integral is indeed 0. Then we get a very interesting observation. That is, here the curve I integrated was this one, and I had a hole here, right? That is, the function is holomorphic on the whole complex plane except this point. So you see, the curve, like so this is my curve, and the function is holomorphic in all the points of the interior of this curve. Then I got a 0 from the integral. So there is this theorem in complex analysis that says that if I integrate a holomorphic function over some closed curve, and all the points that the curve encloses. So if f is holomorphic on all the points that my curve encloses, then I can say that the integral is 0. So let me write the theorem. So the theorem is called Cauchy's theorem. So if f is holomorphic in the region enclosed by gamma, then the integral of f of z dz over the curve gamma is 0. Okay. Yeah. So is the statement of Cauchy's theorem clear to everyone? So when do we get a non-zero output from an integral over a closed curve?
we have a hole.
Exactly. So if
Is that theorem?
no, That's just a consequence of this result, right? So if this is my curve and f is not holomorphic in some of the points inside the curve, so inside the region enclosed by the curve, then I shall get a non-zero output from the integral. Okay, so I forgot to mention an inequality about the integrals. So let's say ML inequality. So this is not related to machine learning, by the way. So, well, yeah. So the ML inequality gives us a bound of the integral. So ML inequality says that the value of this integral is smaller than or equal to m times L. Now, what is m? So m is the supremum of f in, sorry, supremum of f in the image of gamma. Okay. Also, for this theorem to hold, we don't need gamma to be a closed curve. So gamma can be any differentiable curve. And L is the length of gamma. And how do we define the length of gamma? We define the length of gamma to be an integral that goes like this: gamma prime of t, the absolute value of gamma prime of t. So that is the length of gamma. And m is sort of the highest value of f in the image of the curve. I shouldn't really say highest. Well, supremum of absolute value of f. I'm extremely sorry. So this basically means that f of gamma of t, the absolute value of f of gamma of t, is smaller than m for every t. So this is my ML inequality. And the term ML inequality comes from these two, m and l. So m is sort of the maximum that f can, maximum value f can take. Of course, by maximum, I mean that the maximum of the absolute value, or the maximum of modulus, yeah. So f is bounded by m in the image of gamma, and L is the length of gamma. Okay. All right, so we have covered Cauchy's theorem, ML inequality. Then I have Cauchy integral formula. So suppose I have a function f from u to c, and it's holomorphic. And let's take some z0 from u, and I shall further assume that the open ball centered at z0 with radius r, the closure of the open ball is in it. What do I mean by the closure of an open ball? That is, for complex numbers, the scenario is very simple. So the open ball is the interior of this thing, right? And the closed ball contains the boundary of this as well. So that is the closed ball. This is all the z that are distance less than or equal to r apart from z. Okay. Yeah, so R is a radius such that the interior of the open ball as well as the boundary of the open ball is inside U. Sorry. So this is U and this is my closed ball. Okay. And the closed ball is contained in my open set U. Okay. Then I have that for every z in my open ball, I have a formula for f of z. So f of z is equal to 1 over 2 pi I integral of f of w over w minus z dw. So w is my integration variable here, and z is the point I chose from the open ball, and the integration is over the boundary of this open ball, that is z minus z naught equals to r. How do I write this clearly? Yeah. So this is a Cauchy integral formula. So we have a more general formula that tells me the value of f. So that tells me the value of the derivative of f at z. So the nth derivative of f at z is given by another integral that is also over the boundary of this open ball, that is z minus z naught equals to r, and my function is f of w divided by w minus z to the power n plus 1 dw, and I have an n factorial over here. So these two are my Cauchy integral formula. And you can see that from the second one, the first one follows immediately if we choose n equals to 0. If we choose n equals to 0, then this n factorial becomes 1, and this w minus z to the power n plus 1 becomes w minus z to the power 1. N plus 1. All right. Yeah. And from these integration formulas, then we have a very interesting inequality that is called Cauchy estimate. That gives us a bound on an on the nth derivative of z naught. That is, the nth derivative of z naught is bounded by m times n factorial divided by r to the power n. What is m? M. So the absolute the absolute value of z is smaller than m on the boundary of the open ball on z minus z naught less, so equal to r. So if f is bounded by m on the boundary of on the curve we are integrating over, that is the boundary of the open ball, then I have that the nth derivative of z naught is bounded by m times n factorial divided by r to the power n. Of course, r is the radius of the open ball. Yeah. Now I have another theorem that we probably talked about that theorem a little bit in the previous class. So the theorem is Liouville's theorem. So what does the Liouville's theorem say? That is, if I have a function defined on the whole complex plane, and it is holomorphic as well. Also, I need the fact that f is bounded. That is, f of z, the absolute value of f of z is bounded by some constant m for all z. Then f must be constant. So Lewis theorem is a very powerful theorem in complex analysis. So in order to prove that a function that is defined on the whole complex plane is constant, you just need to prove that the function is bounded. So if I have a function that is defined on the whole complex plane, and the function is holomorphic, and if the function is bounded, that is, if the absolute value of f is bounded by some constant, then I can say that f must be constant as well. And obviously, needless to say that this theorem does not hold in real numbers. Can someone give me an example that this does not hold in real numbers? Exactly. So for reals, this is a function defined on the whole real line, and this is bounded as well. We know that f is bounded by 1. But this is not a constant function. So the other day, I saw a thread in Math Stack Overflow that is a thread of the common misconceptions. And one of those common misconceptions was that, so the following. The number one statement is that sin z is holomorphic on the whole complex plane. Okay, so this was the first statement. The second statement, that is, sin z is bounded. Therefore, by Lewis theorem, sin z is constant. So, but we know that sin is not a constant function. So, what is wrong in this reasoning?
I think the sign of z is not
Exactly. So sin is not bounded because
in the exponent in the
exactly
direction is exponential.
right. So we define sin as e to the power z minus e to the power minus z over 2i, something like this. Is it divided by 2i? Yeah. Cos is divided by 2, but sin is divided by 2i, right? So yeah, and here we have two exponentials here. So these two exponentials make sin an unbounded function. Okay. All right. That's it. So now I'm going to talk a little bit about the zeros of a holomorphic function. All right. Let's say I have a holomorphic function from U to C, and I shall call Z naught to be a zero of F. Z naught is a zero of F if F of Z naught is 0. Okay. F of Z naught is 0. So we shall call Z naught as 0 of F if the value of F at Z naught is 0. Very simple as that. Now, we know that all the holomorphic functions are analytic, right? So I have a power series representation centered at Z naught. Okay. So how does the power series look like? It looks like f of z equals to sum of some cn z minus z naught to the power n. Right? The sum runs from n equals to 0 to infinity. Now, some of the first terms of this power series, like some of the first coefficients of this power series will be 0, because what is C0? We know that the Cn is given by the nth derivative of f at z naught divided by n factorial, right? So C0 is f of z0. So C0 is f of z naught, and that is 0. So the first coefficient is 0. So let's say the first coefficient is 0, and suppose the first non-zero coefficient is Cm. So in principle, we can have that C1 is also 0, C2 is also 0, and up to Cm plus 1 are all 0. Then suppose Cm is non-zero. Okay, then we can write the power series as Z minus Z naught, Cm Z minus Z naught to the power m plus Cm plus 1 Z minus Z naught to the power m plus 1 and so on. So we can factor out the Z minus Z naught to the power m, right? So if we factor that out, we have that Z minus Z naught to the power m, and we have a sum that is Cn Z minus Z naught to the power n minus m, and the sum runs from n equals to m to infinity. All right. So we can express this sum as another function, let's say g of z. So we have that z minus z naught to the power m times g of z. Okay. And yeah. Now, can someone tell me if g of z naught is 0 or not? So is g of z naught 0? So what is the value of g of z naught? The value of g of z naught is Cm, right? Because in this sum, if I plug in z equals to z naught here, all the terms where n minus m is at least 1, all those terms vanish. So the only contribution we have is Cm times, well, there's nothing else here. So we get that g of z naught is Cm. And we assume that Cm is non-zero. In fact, our assumption was that Cm is the first non-zero coefficient of our power series. So yeah, g of z naught is non-zero. So from this we have a very interesting observation, that is, if f of z naught is 0, then in some open ball centered at z naught, I have f of z is equal to z minus z naught to the power m times g of z. With g of z naught being non-zero. Okay, so the integer m we have here, we call m the order of 0 at z naught. So m is called the order of 0 of f at z naught. So you can also see this differently. Like, we know that what is Cn? Cn is the nth derivative of f at z naught, and that divided by n factorial, right? So we know that the zeroth derivative, that is the function value of f itself at z naught, is 0. And if m is the order of 0, then I have that the mth derivative of z naught is non-zero, but all the previous ones, like the kth derivative of z naught, is 0 for all k smaller than m. Okay, I should probably write it like more towards the left. So the mth derivative of f at z naught is non-zero, and all the previous derivatives, f k of z naught is 0 for each k strictly smaller than, sorry. So you can define the order of a zero like this as well. Like the order of a zero is the first non-zero derivative. So the first non-zero derivative is the mth derivative here. That's why the order of zero is defined to be the integer m. In fact, it's a positive integer. So m is called the order. So is the definition of order of a zero clear to everyone? All right, now we have talked about the zeros of a holomorphic function, and we defined what an order of a zero is. Now I'm going to define a zero set of a holomorphic function. So if f is a holomorphic function, the set z of f includes all the zeros of f. So that is, it contains all the z naught belongs to the domain of f such that f of z naught equals to 0. All right, so now we have a very interesting theorem that says that z of f does not contain a limit point in U. So what is the limit point? So if we form a sequence out of the elements of z of f, and and if in fact we need to have a like eventually non-constant sequence. So we can ignore the constant sequences. So if we form a non-constant sequence out of the elements of z of f, if the sequence converges, the converging point is not in U. So that is so all those converging points are called the limit points. Okay. So how do we sort of well, we need to use this theorem a lot in near future. So I guess it's a good practice to see how the proof goes. Okay. So let's say we form a sequence Zn, and all of the Zn are zeros of. So all the Zn are zeros of f. So that is f of Zn is equal to 0. And assume for the sake of contradiction that Zn and the sequence Zn converges to some Z prime in U. Okay, so we are assuming that the set Z of f has a limit point. So if the set Z of f has a limit point in U, that means there is some element Z prime in U for which we can form a convergent sequence that converges to Z prime. Okay, now we know that f of Zn equals to 0, right? Because all the Zn are taken from the zero set of f. Then we can take the limit as n tends to infinity. So that limit is also 0. Since f is a continuous function, well, f is holomorphic, so it needs to be continuous. Then we can take the limit in front of the function. So we have f of limit of Zn equals to 0. And what is the limit of Zn? The limit of Zn is Z prime. So we have f of Z prime equals to 0. And also, we have assumed that Z prime is in U. And f is holomorphic on the set U. So then f is also analytic as well. Then, well, I don't know. We don't need analyticity. So let's say the order of 0 at Z prime is, let's say, m. Then we can define like f of z equals to z minus z prime to the power m times g of z, such that g of z prime is non-zero, right? So that was the definition of order. So here we have a hidden assumption is that f is not identically 0. Okay, so if f is identically 0, then the 0 set is the whole open set U, right? Then we trivially have like limit points. So here we have an assumption is that f is not identically 0. Okay, so yeah, so by the definition of order, we can basically factor out the z minus z prime to the power m, and yeah, and like this. So this holds in some open ball with radius r. Okay. Now, since the sequence Zn converges to Z prime, so if this is my Z prime and we take an open ball with radius r, then by the definition of convergence, eventually the sequence Zn will be in this open ball, right? So Zn is in the open ball for n greater than, let's say, some big n. All right. Now, since all the Zn are the zeros of f, then we have that f of Zn. Thank you so much. So we have that f of Zn is 0. And yeah, and for this Zn, this equality holds, like this one. So since all the Zn after some big n, all the Zns are inside this open ball, that's why we have this equality holds for this Zn, right? And we know that f of Zn is 0, and f of Zn is equal to, by the above inequality, Zn minus Z prime to the power m times g of Zn. Okay. Now, none of these are 0. But this is 0, but the product is 0. That means g of Zn equals to 0 for all n bigger than this n. Okay, now from this, what conclusion can we draw? Let me zoom out a little bit. Sorry. So what was our Z prime? No, yeah, Z prime was the, so from the beginning, we have assumed for the sake of contradiction that the 0 set has a limit point. So if the 0 set has a limit point, then we can form a sequence in the 0 set that converges to that limit point. Okay, let's say Z prime is the limit point and my sequence is Zn, right? Then we must have that f of Z prime is also 0 by the continuity of f. Then suppose the order of 0 at Z prime is m. So by the discussion above, we can factor out the Z minus Z prime to the power m. Then we have this, and we also have g of Z prime is non-zero. Okay, so g of Z prime is non-zero, and this equality holds in some open ball centered at Z prime. So since our sequence converges to Z prime, after some big n, all the terms of the sequence are inside my open ball. So for all these Zn, where the small n is bigger than the capital N, for all those terms, this equality holds. So this equality holds And if I plug in the value of zn in this equation, I get that f of zn is equal to zn minus z prime to the power m times g of zn. Since f of zn is 0 and this thing is non-zero, then I must have that g of zn is 0. Then since z is the limit of zn, and we can take limit here as well. So limit n tends to infinity g of zn, this is also 0. And my g is continuous, so I can basically take the limit inside of the function, so I have that g of z prime is 0. So which is a contradiction. Okay, is the proof clear to everyone? So that means if my holomorphic function is not constant, then its zero set cannot contain a limit point. So oftentimes we say those sets that do not contain a limit point, we call those sets discrete sets. So the zero set of a holomorphic function is a discrete set. All right. Now we have another theorem involving zeros of holomorphic function. The theorem says that, let's say I have a holomorphic function f from u to c, and like as usual, u is open and connected. U open connected, and if there exists some z naught inside u such that the nth derivative of z naught, the nth derivative of f at z naught, the nth derivative of f at z naught is 0 for all n. For all n bigger than or equal to 1, then f is constant. So this is a really powerful theorem. And of course, this only holds in complex analysis. For real functions, for real valued functions, this of course does not hold. And we have seen the example earlier that the function e to the power negative 1 over x squared. So at 0, all the derivatives of that function are 0. But nevertheless, the function is not a constant function. All right. Also, for this theorem to hold, we need the fact that U is connected. Because if U is not connected, let's say it has two connected components. So we can have that F is let's say constant 1 here, and F is another constant here. F is, then the whole function F is not a constant function because it has two different values. But if I take a point here, then all the derivatives of f at this point are 0. So that's why we need the domain to be connected. All right, and now I have a couple more theorems about holomorphic functions. So this one is called maximum modulus principle. Maximum modulus principle. So what this maximum modulus principle is saying is that so let's say I have a holomorphic function from u to c. Then if there exists some z naught in u such that the modulus of f at z naught is maximum. So by maximum, I mean that if I draw an open ball centered at Z0, then and inside that open ball, like among all the points in that open ball, the modulus of f at Z0 is the highest one, is the maximum one. That is f of Z0, the modulus of f of Z0 is bigger than or equal to f of Z for each Z belongs to some open ball. So, the statement is basically saying that, well, I haven't finished this statement yet. Let me finish it first, then I can explain it again. So if this holds that if there exists some if there is some complex number in my domain such that the maximum of the function is highest at that point, then f is constant. So that means if there exists some number z, some complex number z0, and some open ball centered at z0, such that inside that open ball, the modulus of f is maximum at z0. If the modulus of f is maximum at the point z0, then we must have that f is a constant function.
It's a local max.
Yeah. So the modulus of f is locally maximum at z0. So if this happens, then f must be a constant function. And obviously, needless to say, this is not true in real numbers. Like you can create a, well, yeah. So of course, if for sin x, so at this point, so the absolute value of sin x is locally maximum, right? So I can form an interval centered at this point. This is pi by 2, right? Yeah. So the absolute value of f is locally maximum at pi by 2, but nevertheless f is not constant. So this is the maximum modulus principle, and we have another result similar to this one, that is the minimum modulus principle. Minimum modulus principle. So as expected, the theorem basically states that if we have a point where the modulus of the function is locally minimum, then the function has to be constant. So, but here we need to have another condition, because you see, like, if z0 is a 0 of f, then f of z0 is 0, right? And the modulus of f of z0 is 0, and it is the minimum one. So let's say if I form any open ball centered at z0, the modulus of f of z0 is minimum in that open ball. But we can have non-constant functions as well, right? So we need to impose another extra condition, is that f of z0 is non-zero. So I'm going to now state minimum modulus principle. So this is a side note. This was a side note. So let's say f is a holomorphic function from U to C, and if there exists some z0 inside U such that, first of all, f of z0 is non-zero and f of z0 is minimum for all z in some open ball, for all z belongs to the open ball centered at z0 with radius r. So if this happens, then f is constant. So is the statement of maximum and minimum modulus principle clear to everyone? So as you can see, holomorphic functions are like extremely powerful. Or you can say that they are like very restrictive as well, because, well, I can, huh? Yeah. So you can say that the holomorphic functions are very conservative. So we cannot have a function defined on the whole complex plane that is bounded, because if that happens by Liouville's theorem, the function is the function becomes constant, right? So we cannot have locally maximum modulus, like, because if we have locally maximum modulus, then the function becomes constant. We cannot have locally minimum modulus. So yeah, so basically holomorphic functions are very powerful and restrictive. So that's why we need to sort of weaken the holomorphicity condition a little bit. Now, in order to do that, I'm going to start with a motivating example. That is, I'm going to define what an elliptic function is. Elliptic function. So we call a complex valued function an elliptic function if sorry, I need to define another terminology first. So let's say I have two complex numbers that are linearly independent. Let omega 1 and omega 2 are complex number. So by linearly independent, I mean that they are linearly independent as over the real numbers. That is, the ratio of omega 1 and omega 2 is not a real number. So their ratio is a complex number that is not a real number. So, exactly. So if this is omega 1, then the omega 2 is not on this line. The omega 2 is in a different line. So since omega 1 and omega 2 are two linearly independent vectors, then all the complex numbers can be written as a unique linear combination of omega 1 and omega 2, right? So all the z can be written as some alpha omega 1 plus beta omega 2, where alpha and beta are real numbers. Okay. Now I'm going to define what an elliptic function is. So we call a complex valued function f an elliptic function with respect to these two complex numbers. So f is an elliptic function with respect to omega 1 and omega 2 if the following condition holds. That is, f of z equals to f of z plus omega 1 equals to f of z plus omega 2. Okay, f of z plus omega 2 for all z. So if these two equalities holds for all z, we call f an elliptic function. Yeah, it's a doubly periodic function. And suppose we are looking for some very nice elliptic functions that are, let's say, f is defined on the whole complex plane and f is holomorphic. So now we are looking for such elliptic functions. Then what we have is that, well, it exists because, well, any constant function. If I take a constant function, then all these conditions are satisfied. Okay. Yeah. So what I was gonna say is that, let's say this is my 0, this is omega 1, this is omega 2. and this is the parallelogram formed by these two numbers. And this point is omega 1 plus omega 2, right? And then I can have another copy here, here, yeah. And as I said, if I take a if I take any complex number, so that complex number can be written as alpha omega 1 plus beta omega 2, right? And these alpha and beta are real numbers. Now, so we know that f is doubly periodic, right? So f of z is the same as f of z plus omega 1, and that is the same as f of z plus omega 2. That is, in this point, the value of f in this point is the same as the value of f in this point. And that is equal to the value of f in this point as well. So that is also same as the value of f in this point, and if we extend it, the value of f at this point is also equal. So that means, so we can, so if we know the value of f in this parallelogram formed by 0, omega 1, omega 2, and omega 1 plus omega 2. If we know the value of f in this parallelogram, we know the value of f on the whole complex plane. Why? Because if I have z equals to this, then well, I can write this as the floor of alpha omega 1 plus the floor of beta omega 2 plus the fractional value of alpha. You write it like this, right? So these are so basically floor of alpha plus the fractional value of alpha is equal to alpha. Okay, and these two numbers, they are in the interval 0 to 1. All right, and the floor of alpha and beta are integers. So f of z is equal to, well, f of z minus omega 1, right? So, and we can subtract like the floor of alpha many copies of omega 1. And similarly, we can basically subtract floor of alpha times omega 1 and the floor of beta times omega 2. So this is omega 1. So then we get that the f of z is equal to some point here. So that means if we know the value of f in this parallelogram, we know the value of f everywhere. Now, yeah, and this parallelogram, including the boundary as well, so yeah. So this parallelogram is what we call a compact set. So a compact set is basically a closed set and bounded. So this is a closed set, and this is bounded as well because we can bound it inside some closed wall. Okay. Also, one thing to remember is that the definition of compact set is not closed plus bounded for general topological spaces. So this is only true for the spaces we are interested in. So, yeah, and there's a theorem in real analysis is that if I have a continuous function on a compact domain, the function is bounded. So here I'm considering my function to be I'm considering my function to be the absolute value of f. And since this parallelogram is bounded, since this parallelogram is compact, we can say that this function is bounded. That is, the absolute value of f is bounded by some m for, well, let me call this parallelogram P. The absolute value of f of z is bounded by m for z in P. And we know that, like, for any complex number, the value of f at that complex number is equal to the value of f inside for some points inside this parallelogram, right? So we can basically say that f of z smaller than m for any complex number. That is this. So we know that a continuous function on a compact domain is bounded. So m is the bound. So yeah, we get that f is bounded, and f is defined on the whole complex plane.
Constant.
So by Liouville's theorem, f is a constant function. And elliptic functions are really interesting for people working in complex geometry or number theory. So yeah, so we have that. We don't have any like non-constant nice elliptic functions. So that's why the condition we were requiring earlier, that f is holomorphic. So this condition is very strong. So we need to weaken this condition a little bit. Yeah, sure. Go ahead.
If we have a periodic function, like single periodic function, we can naturally define a functional circle.
We can naturally define a functional circle, right?
So I can see this like you can naturally define a functional torus because
Exactly.
so are these actually related?
Yeah. So you can consider an elliptic function to be a function defined on a torus, because the value of the function in this line is equal to the value of the function in this line as well. And the value of the function here is equal to the value of the function here. So we can basically glue this line, and we can glue this one and this one as well. So then what we get is a torus.
So we can like visualize elliptic function in the torus.
Well, not really. We have that our domain is a torus, right? So inside the domain we can have basically anything. So yeah, so basically we need to weaken the condition of holomorphicity. But okay. Also, a little while ago we saw that if I have a holomorphic function, the zero set of the holomorphic function is discrete. That is, the zero set does not contain a limit point. Now, if the zero set is empty, then what we have is that the reciprocal of the function, this is holomorphic. So if f of f is non-zero, then we can take the reciprocal of f, and the function we get is a holomorphic function, given that f is a holomorphic function, right? But if the zero set is non-empty, then what we have is that then
So you define one of the f acting on z and one over f on z.
right. So 1 over f, this is a function, so this acts on a point on u, and this gives us 1 over f of z. So if my the zero set of f is non-empty, then this is a discrete set, like as we discussed earlier. So this is a discrete set, and we have that 1 over f is holomorphic on u minus z of f, right? Because we can basically define the domain of f to be u minus z of f, right? So we can define 1 over f. We can define 1 over f on u minus z of f, and that function will be holomorphic. And what about the values inside this z of f? So let's call 1 over f to be g. Okay. Then if I take some zi inside this z of f, then f of zi is 0. F of zi is 0. And well, g of zi is not defined, right? Because, well, 1 over 0 is not defined. But if we take the limit as z goes to zi, what do we get? What is that limit? Where? Yeah, limit z goes to z. Yeah. Because g of zi is not defined because it's 1 over 0. So what is this limit? Z. So yeah, so we get that 1 over f that is holomorphic on our open set except a discrete set. And in that discrete set, I have that like g, like the value of g on that discrete set is infinity. Okay, so such points are called poles. So what is a pole? A pole, so sorry, let f from u to c is holomorphic, and a point z naught in the closure of u. By closure of u, I mean that like u and like u along with all the limit points, of u. So this is the closure of u. So you can visually consider it as u along with the boundary of u as well. Okay, so a point in the closure of u is a pole of f if f of z, the limit as z goes to z naught is infinity. Okay. So is the definition of a pole clear to everyone? So a pole can only be on the boundary of my domain, because I have already said that f is holomorphic on my domain. So inside this open set, f is holomorphic. But on the boundary of the open set, I can have a pole. So yeah. Now I'm going to define I'm going to define something that is less powerful than a holomorphic function. So such functions are called meromorphic. Meromorphic function. So we call a complex valued function meromorphic on some open set U if the following conditions hold. That is, there is a discrete set Z in U. Okay, and F is holomorphic on U minus Z. Also, F has poles in Z.
Discrete sets is not the discrete in the homological sense. It's discrete in the sense that
It does not have any limit point in U, right? So you can see that if f is the holomorphic function, then 1 over f is a meromorphic function, right? Like we have seen it here. That is, if f is the holomorphic function, then its zero set is a discrete set. Discrete in the sense that it does not have any limit points. Then if I take the function 1 over f, that function is holomorphic on u except the set of zeros. And we also saw that the limit of g in the discrete set is infinity. That is, all the points in the discrete set z of f are poles of g. Okay, so that is 1 over f is a meromorphic function.
So meromorphic is basically holomorphic, but those are
Right. And there's a very interesting theorem that says that if I have a meromorphic function, I can write it as a ratio of two holomorphic functions.
So they are like the rational function.
Rational functions. In order to define rational functions, I need some, let's say, ring here and some, yeah. So rational functions of what? Rational functions of holomorphic functions. Well, we can say that. All right, now, yeah. Now we are going to analyze the poles of a meromorphic function. So let's say we have a meromorphic function f on an open set U, and let Z naught be a pole. How much time? Of f. Then f admits some sort of a power series around Z naught. So that is not quite a power series. That's called a Lorentz series. So if Z naught is a pole of f, then for Z belongs to some open ball centered at R, but we are not interested in the center. Sorry, some open ball centered at Z naught with radius R, but we are not interested in the center because we know that at the center f of Z naught is basically infinity. So f of Z is equal to some Cn Z minus Z naught to the power n, and this n goes from negative infinity to infinity. And this is called the Lorentz series. So if we have a pole of a meromorphic function, around that pole we have a Lorentz series. And of course, this Lorentz series converges absolutely and uniformly. And in fact, we have another theorem that says that if Z naught is a pole, then we have a fixed number that is. Let me try to draw something.
So you convert it in a function.
Yeah, it converges in this open ball with the center dilated. Okay, so this is 0, this is 1, 2, 3. So yeah. So all these coefficients of this Lorentz series are indexed by the set of integers, right? So we have a theorem that says that if Z naught is a pole, then there is some negative integer here, such that all the integers to the left of this integer, so those coefficients are 0. So essentially, we have a Lorentz series that starts from here, from this integer. Let's say that is negative m. So I'm going to state it now. So if Z naught is a pole, there exists some negative m in Z such that C sub negative m minus k is 0 for all k bigger than or equal to 1. So in some sense, I have the concept of a first non-zero coefficient. So by first, I mean that all the previous ones are 0. So the Lorentz series basically starts from C sub m. So I can basically write the Lorentz series as C sub n z minus z naught to the power n, and the sum starts from negative m and goes up to infinity. So also we can basically factor out the z minus z naught to the power minus m here, right? Z minus z naught to the power minus m, and then we have that sum of Cn z minus z naught to the power, well, n plus m, right? N plus m, and this negative m is called the order of the pole at z naught. So this negative m is called the order of pole at z naught. And also here's an interesting observation, that is, if we can factor out the z minus z naught to the power negative m, we can basically write it like this: z minus z naught to the power negative m times sum of some an z minus z naught to the power n. Okay, yeah, and this n runs from 0 to infinity. I have basically shifted the indices. And then, so since this is the power series, so this is a power series. So the function that this power series describes, that function is a holomorphic function. So sum of an z minus z naught to the power n, sum runs from n equals to 0 to infinity, is holomorphic. So that means if I have a meromorphic function that has a pole at z naught, I can basically factor out some z minus z naught to the power negative m such that the other factor is holomorphic. And the other factor is holomorphic on z naught as well. For on the open ball centered at z naught with radius r. Okay. Can I have 15 more minutes of your time? 10 to 15 more minutes would be sufficient, I guess. Okay. So we have seen the definition of a meromorphic function, and we know that if we integrate a holomorphic function over a closed curve such that all the region the path encloses, so if f is holomorphic in that region, then the value of the integration is 0. Now we are going to see if that holds for meromorphic functions as well. Well, our intuition says that that should not be true. So let's say, suppose f has a pole at z0. Okay. So that is, I can write f like this, like this. And let's say I'm integrating f over some path gamma, and gamma is basically the boundary of this thing, the boundary of the open ball centered at z0 with radius r. So gamma is z minus z0 equals to r. Okay. Then we are going to see how, like what is the value of this integration. Okay, since f has a pole, we can basically form a Lorentz series around z0. So that is summation of Cn z minus z0 to the power n, where n runs from negative m to infinity, right? Now, yeah. So for now, let us assume that we can swap this integral and sum. Okay, we are not justifying why we can swap the integral and the sum, but yeah, let's suppose we can do that. Integration of gamma, well, and since Cn is a constant, so we can bring the Cn outside of the integral, and we have that z minus z0 to the power n, and dz. We have done integrals like this in today's class, right? We have done integral of z to the power n over the unit circle. So we get that if n is not negative 1, then the integration is 0. Then the integration of z minus z0 to the power n over gamma is 0. And what was the value of the integration for when n was negative 1? Yeah, it was 2 pi I. So all the terms with n not equal to minus 1, they contribute 0. So the only non-zero contribution is from n equals to negative 1. So we have that is equal to c minus 1 times 2 pi I. Okay, so we get that c minus 1 is equal to 1 over 2 pi I times f of z, the integration of f of z dz over gamma. And this c sub minus 1 is called the residue of f at z0. And we write it like this, res f comma z0. So this basically measures how much the Cauchy's theorem fails. Okay. And for holomorphic functions, since we only have a power series, we don't have a Lorentz series, right? So for holomorphic functions, we have that all the negative indexed coefficients, they vanish, right? So that's why for holomorphic functions, the residue is 0. So here we examined a case where this was a pole, and this was my was the curve I integrated over. Also, Also, we had another assumption that was that in this region there is only one pole. Okay. So do you all see where we use this assumption? Because we said that where where is it? Yeah. So we said that G is holomorphic on the whole open ball, right? So outside of this center, so if I multiply a holomorphic function with another holomorphic function, so this is holomorphic everywhere except the center. Right? So this product that is holomorphic on the whole open ball except the center. Right? So we use this assumption that inside the region the curve encloses, there is only one pole. Now, what about multiple poles? So we also have another theorem for this. Let's say this is my curve gamma, and there are multiple poles here. So this is Z1, this is Z2, and there are multiple poles. Then we have the integration of f of z dz over gamma, and if I divide the value of the integration by 2 pi I, we get the sum of residues at these points. So we get sum of residue of f at zi, and we have a summation over I. And zi are the poles in the region enclosed by gamma. So you can sort of think about this as a generalization of this. So a generalization of this equality is this one. Okay, so is there a name for this theorem? Well, yeah, this is the residue theorem. So this is the residue theorem. Okay. Now, how do we calculate residues? So we have multiple cases. Suppose if the pole has order 1, the pole at Z0 has order 1. Well, we call these poles simple poles. So if the pole has order 1, I define the residue of f at Z0 to be z minus Z0 times f of z, and limit of this as z goes to Z0. So this, well, by order 1, I mean that it should be order -1, because we define the order of pole to be a negative number, right? So we define -m to be the order of the pole. So if the pole has order -1, well, this should be intuitively clear, because if we expand f into Lorentz series, since since z0 has order -1 as a pole, I'll only have c sub -1 z minus z0 to the power -1 plus c sub 0 plus c1 z minus z0 plus and so on and so forth, right? This is f of z. So since the pole has order -1, I don't have any coefficients before c sub -1, right? And we need to find like c sub -1. So if we multiply this thing by z minus z0, then f of z times z minus z0, this is c sub -1 plus c0 z minus z0, and so on and so forth. And if I take the limit as z goes to z0, then all those terms vanish. We only have this one. So that is why the residue of f at z0 is equal to this limit. Now if the pole has order like larger than 1, or should I say smaller than -1. So if order not -1, then we have a slightly more complicated formula. The residue of f at z0 is equal to 1 over n minus 1 factorial z So let's say order is negative n. Okay. Limit as z goes to z naught, then the nth derivative. Well, this is a very long equation, so it's better if I write it in the next line, I guess. So 1 over n minus 1 factorial, the limit of z goes to z naught, the n minus 1th derivative of the function, that is z minus z naught to the power n times f of z. So this is the formula for calculating residues when the pole is not a simple pole. Well, we can apply this formula for simple poles as well, because if we plug in the value of n equals to 1 here, then we have z minus z naught times f of z, and the 0th derivative is the function itself, and the 0 factorial is 1. So yeah. Do you have any questions about the residue theorem or the two different ways I showed for calculating residues? All right. So now I have one final theorem. No, this is not the final theorem. So I have two more theorems. So one is called the argument principle. So what is the argument principle? So the argument principle says that suppose I have a meromorphic function. Oh, this is not a good notation because f is not defined on the whole of U. F is defined on U minus a discrete set. So f is a meromorphic function, and yeah, gamma is a closed curve that does not go through any of the zeros or poles of Z. Not through any zeros or poles of F. That means, suppose this is the image of gamma, then F is, F is neither 0 in this curve nor F has a pole in this curve. Okay, so gamma does not go through any of the zeros or the poles. Then we have that, then 1 over 2 pi I, the integration of gamma of f prime of z divided by f of z dz equal to sum of order of zi. What are zi's? So zi's are the zeros or poles in the region enclosed by gamma. Okay. Yeah. So zi's are the zeros and poles. Zeros and poles. Where? In the region enclosed by gamma. In the region enclosed by gamma. Okay. So this is argument principle.
Zeros and poles of f of z. Right?
Yeah. All right, now I have one final theorem, then we're going to call it a day. So that theorem says that, I should have mentioned it earlier, but somehow I forgot. That is, suppose I have a sequence of holomorphic functions. And the sequence converges to some other function uniformly. So then the uniform limit is also holomorphic. So in real analysis, the uniform limit of a sequence of continuous functions is also continuous. But and the uniform limit of a sequence of differentiable functions may not be differentiable in real analysis. But for the complex case, this is true. Okay. So that concludes our discussion on complex analysis. Does anyone have any questions? So I'll scan and upload this to our Discord channel. Okay. Oh, I need to take attendance.